I'm your host, Professor McKinney. Um, all right, so let's recap where we were last time. We started talking about uh, parametric equations and sort of just briefly how to put this. We're um, motivating sort of the idea of how we're going to do the calculus with this stuff. So let's just get to it here. So first thing I'm going to do is, so let me define, suppose that I have a function, okay, and the function I'm going to call f, and I'm going to put a little arrow over f because what kind of thing am I spitting out? Okay, so f takes in a value t and outputs two values, an x-coordinate and a y-coordinate. And x coordinate is given by what function? Little x of t, and its y coordinate is given by little y of t. Okay, whatever those things are. Okay, so when I write it that way, what I've done is I've actually sort of defined this as a vector function. Now, let's think back to high school, right? In, say, pre-calculus or physics, or maybe both. You guys all seen vectors? Yeah? Okay, good. So, but if you know, we want to just think of it, it's really just an ordered pair, right? It's a point, okay? And a vector is sort of an arrow that starts at the origin and ends at some place, and so all I have to specify is where the end point is, okay? Okay, so what I want to define then is I want to define the derivative of this thing. Okay, so f prime of t, if you will. Now, how would I define that? Well, what do you think I should define it as? Right, let's just take the derivative of x and the derivative of y. So all I've done is I've taken the derivative of each coordinate. Okay, and I'm going to get whatever I get. Now, so what this has done is I've defined the derivative of this function f, which is this new category of objects, namely it's a vector value function, in terms of the derivatives of x of t and y of t. Well, x of t and y of t are just formulas involving t. Those are like top one looking functions. So we know how to take the derivatives of those. Let's do it. Okay, so this is still a vector object. Now, if I want to know, like, let's go back to top one. When we talk about the derivative, what did we talk about that was associated with it? The slope of tangent lines. Okay. So if we say the derivative is the slope of the tangent line, well, that's no longer true because I don't have a number there. I have an ordered pair. Okay? That's not a slope. So how do I take this and produce a slope? Well, what is slope? Rise over run. Okay? So the slope, which we call m, or maybe we wrote this as dy dx, is going to be y prime of t divided by x prime of t. Okay? Rise over run. And there's another way that we can see why that is what it should be, which I'll write in a moment. Yes? If you do the ratio of them, right? So if you take, you've got a point x comma y, but it's a formula involving t. Right? You take each coordinate's derivative. If you do the derivative of the y coordinate divided by the derivative of the x coordinate, that is the slope. Okay. we'll see that in a minute when we do an example. Okay. Okay, now here's another reason why we should think of it as this. Because of the chain rule. Okay, so chain rule says this, right? dy dx is dy dt times dt dx. Okay, and this is the benefit and also extreme drawback of Newton's style notation, because what does it look like I'm doing with dy dt times dt dx? I'm canceling the dt's. That's what it looks like. Now, am I really canceling the dt's? Not really, but it kind of looks like that. So, yeah, this is what we call a reduced notation. You know, which of course makes me want to form like a people for the ethical treatment of notation, right? Kind of like an advocacy group or something. You know, for only $1 a day, you could feed, clothe, and educate a neglected piece of mathematical notation. Mm-hmm. Yeah, it'll get lots of. You can't hear me, Mr. Hoke? What do you mean you can't hear me? I definitely am transmitting. Check your audio. Make sure you're doing it. Let me turn on my audio here. Okay, so I'm going to start saying things, and hopefully my speakers will all hear myself. Blah, blah, blah. Oh, it would help if I weren't muted here. Okay, let's try that. Okay, no, I'm definitely translating, pardon. So I'm not sure what the problem's got to be on your end. Yeah, Cole.
Why does it dip slowly with one? It goes, you go from talking to dead silence. So how does it just dip slowly?
It probably has like a fall off curve kind of thing. Okay, so right, so the chain rule basically is what explains this. But another way to think about it, right, is that uh, the vector x prime comma y prime is exactly a run comma a rise. Well, what's the slope? Rise over run. Right, good stop. Okay. All right, so let's take an example here. And let me just use a simple example from last time. So if f is cos t comma sine t, what did that draw if we graph it? We are circle. Radius 1, centered at the origin. Which way did we go around the circle? We went around counterclockwise. Okay, great. So what is f prime of this thing? Well, indeed.
Sine t.
Okay, thank you, Cole. Thank you. Yes, beautiful. Okay, Cole for the 360 no scope. Yeah. Flush. Okay, now how many of you guys in the room did not get that? 360 no scope? You get it? You get it, Donovan? Do you get that? Okay. Yeah. Jack, you get it? Okay, everybody gets it? All right. So, in my many years of teaching, right, so here's what's crazy. This is my 10th year, I'm in my 10th year now at Wabash, and my 11th year professoring. Right? And you know what's been true for all that time? Most of the time you guys don't get my jokes. And it makes me very sad.
You still have to keep firing.
Yeah.
Because you're like a good tutor. You just don't care. Keep going. I respect it.
Well, I hit the target whether or not you guys. I actually missed the shot. what happens when your thought is in the ring, right? You're a pretty good marksman. Anyway, okay, so there's our thing. So let me flop over here to Mathematica, and I want to graph this a little bit, okay? And I want to kind of see what we're working with. Um, God, I hate the sound of my own voice. Do you get, am I the only one? Like, when you guys hear recordings of yourself, do you think, man, do I really sound like that? Yeah.
About that, am I allowed to share what?
Please, as long as it's not vulgar.
So, like, when you talk, the lower vibrations in your voice, nobody else will decide to you. So you think you sound deeper than you actually do.
Okay.
And I felt the same way until I started mentioning things. People were like, you sound good. So I'm like, okay. But I think you sound great. So
You just don't like the way I dress. Like cigarettes, do you?
yeah.
Okay. All right, well, let's get over to Mathematica. So what I'm going to do is I'm going to define a function. Okay? Yeah, I know, right? Cos t comma sine t. And on paper, I wrote parentheses here for vectors, but in Mathematica, I have to use curly braces for vectors. That's just, right, but you, hopefully by now you guys are used to it. There's handwritten notation and there's Mathematica notation. Wouldn't it be great if they matched? Mm-hmm. Yes, okay. You build me a time machine and I'll make sure they match. Now I can't say that I wouldn't go back in time with the sports almanac and maybe bet on a few games and make a lot of money. But yeah, okay, you guys do get that reference right from Back to the Future? Okay, just checking. All right, so, all right, and then I'm going to define, well, let me just call it g of t to be the derivative. Okay, and now what I want to do is I want to plot, or well, actually parametric plot. Parametric plot is when you're plotting parametric functions, and regular plot is if it's y equals f of x type thing. And then I just need to specify the range of t. Okay, so not shockingly, right, we get this. Okay, that's the plot of the original function. It's our original circle. Okay, now, if I plot on here g of t, I get the same circle. Okay, that's partly coincidence because of the function that I picked originally. But let's think about, though, what is g of 0? Circle with sign of 0. 0. Okay? So it's 0, comma 1. Right? Okay, what was f of 0?
1 comma 0.
Okay, so the parametric plot, the graph looks the same, but where does the plot of g start? It starts at the top of the circle rather than the right end of the circle. Okay. The other thing is which direction does it go? Well, as t increases, what is true about the torment g of t? 1 and it decreases, and the sign is going to start at 0, and it would increase except there's a negative in front. So it's still going to go counterclockwise, it just starts at the top instead of at the right. Okay? All right. Now, I'm going to do some fancy stuff here. Okay, so behold. Behold. Okay, so I'm going to make this back to f of t, and I'm going to say p1 equals this, and then fasten your seatbelts, boys. Um, Let me pick a point. So pick a value of t. Let me do just pi over 4. How about that? Okay. And now what I'm going to do is I'm going to show 1 and 2. Okay, so at pi over 4, where am I? I'm at 45 degrees, that makes sense, right? And where am I on the circle in my parameterization? I'm at the end of that little arrow. Yeah? Okay. So I've used the arrow tool and the graphics thing, right? Because I want to think about my position as really being a vector. I'm some distance from the origin. It's, in this case, the distance is always 1, makes sense, it's a circle. But I am at the end of that little arrow. And if I change the pi over 4 to some other value, then I just be at some other point in the circle. Okay. What I'm interested in, though, is what is g of pi over 4? Okay, so I'm going to make a copy of this thing. Oops. And I'm going to call it P3, and instead of doing F, I'm going to do G, okay? So that's the derivative, okay? Now, I'm also going to graph here P3. Okay, so, and I could sit and go in here and color code these so you can tell the difference between them pi. Just leave it like that to write this instance. So, the one that's pointing to the right is my position. The one that's pointing to the left is my derivative, okay? Now, what did you guys learn about vectors in high school? Okay, good. What else? That's definitely true. What else did you learn about vectors? Okay, they have coordinates. Okay, and the negative means what? The vector. Right, if you make a vector, it just flips it around. Okay. What else? So both of the vectors I've drawn here start at the origin. Do they have to start at the origin? No. Okay, so if the vector, as long as the vector points in the same direction and has the same length, it's the same vector. Okay? So let's take that vector that's pointing from the origin sort of up and to the left. If I slide that vector around so that it starts someplace else, but I make sure it points in the same direction and I make sure it has the same length, these are the same vector. Yeah. Yes. Okay. So what I choose to do is to slide this thing so that its tail is at the tip of the position vector. No, just watch, okay? Okay, so that's where I'm going to move it because I'm going to add like so. Okay, now it's gotten cut off a little bit, so let me reorder. Okay, there we go. Okay, so what's happened here? Well, what's the vector that's inside the circle? It goes from the center of the circle, which is where we put the origin, to a point on the perimeter. That's our position vector. Okay? The second vector that I've drawn here, do you guys agree that that vector that's sort of on the perimeter of the circle is the same vector as I had a moment ago? Does it point in the same direction? Oh, it does. It does. Is it the same length? Yep. And so what is that vector? The whole, it is tangent. It's the velocity vector. Right? Okay? So the derivative here means the velocity. That makes sense. What did it mean, F1? Okay, but, and I think we mentioned this last time, what's the difference between velocity and um, speed? Jack? 360 no scope? Okay, yeah, velocity is a vector, meaning that it has direction and it has magnitude. Speed is a scalar, it's a number. Okay, amongst other things, speed can never be negative. The definition, this is the rate of something. Yeah. When you run around the track, you have to no, you have linear velocity. It's the instant time for the track. No. That would be the net change in position. Yeah, if you run all the way in like a oval, how do you go anywhere? You didn't have that. Well, okay. Over a period of time you did, but instantaneously you did. Right, yeah. Right. So you have no average. Yeah, there you go. Right. And that's the difference, average versus instantaneous. What are we in the business of talking about in calculus? Instantaneous, right? That's the whole point of the derivative. If all you wanted to talk about was averages, you'd still be back in algebra in high school, right? But we've moved on from that. We're big boys and girls. Well, big boys. And, yeah, okay. All right, so that thing is the tangent vector. Now, could I get an equation for the tangent line based on that? Sure. What information do I need to talk about a line? A couple ways to look at it. Well, I need a point and I need a slope, right? Do I know a point? Yeah. Wherever we are on the circle, do I know a slope? Well, what's the slope of that tangent vector? It's whatever its rise is over whatever its run is. And in this case, because I picked a nice number, what's the slope of that thing? -1, right? Because it goes up 1 unit and over, or up some amount and to the left that same amount, and so the ratio is -1, because the slope of the left is considered negative. Okay, does that make sense? Okay, so there's my velocity vector. Okay, Gucci? Yes, Jack. Okay. Well, so like, let's say that I had an object like a string and I was twirling it in the air, right? Well, the velocity vector has to obviously physics meaning, and the position vector definitely has meaning. Where the thing is, right? The velocity vector means which way is it pointing, which way is it going at that instant in time. Okay? And so if I'm twirling the thing around so that I get a circular motion like this, well, maybe here's another way to think about it. What would happen if I were twirling the thing around and the string broke? At the instant the string breaks, what would happen? It would keep going in that same straight direction, right? Don't you break fictitious forces into this classroom? Oh yeah. It's kind of like that The Simpsons when Lisa invents a perpetual motion machine, and the Homer is like, "Young lady, in this house, we obey the second law of thermodynamics." And it's like Homer would never actually say that. Okay, so the that's the meaning of velocity in that case, right? Now let's apply this to a problem that we looked at last time. Okay, last time we did projectile motion. Okay, so last time I've already used F and G. Okay, so let me use a new name here. We had a thing where we said, okay, right? This was our projectile motion problem that we looked at last time, and I think those were the same numbers we picked. We picked pi over 4 because Cole remembered that that maximizes the range, and I picked an initial velocity of 10, just basically cause, and then we've got our gravity term. All right, so if I plotted that thing again, let's just do oops, something like that, right? And we found that it was like, what, 1.5 seconds roughly before the thing hit the ground again? Yeah? Okay. All right, so in terms of calculus, what were we interested in? How could we, for example, find where this thing is at its peak? Well, what would happen at the peak?
The VXL is saying you have no V.
Yeah, exactly. So at the peak, there is still velocity in the x direction, but there's no velocity in the y direction. Yes? Okay. So um, let's take the derivative of the position function. Okay, so the velocity function in this case is that. Okay, first off, how did we get that? Why is it just 5 root 2 in the x coordinate? Well, what's the derivative of something t? Just the something, okay? But our cosine term there is cosine of pi over 4. What is cosine of pi over 4? Root 2 over 2 times 10 is 5 root 2. Okay? And that's only because we take a specific angle, or rather pole here. Okay? And then similarly for the y coordinate, right? Well, we've got the front term, which we already know what to do there. And then what's the derivative of minus a half 9.8t squared? Well, minus 9.8t. That's the gravity part. Okay, so that function there, 5 root 2 comma 5 root 2 minus 9.8t, that is our velocity function. Okay? Now, what are things you notice about that, by the way? Just looking at that function, what's interesting?
The graph velocity.
The graph is position. I have the graph velocity. Yeah, just need to get one before. Okay. Huh? Yeah, okay. Well, that's only because you picked 45 degrees. Well, surely you can tell me more than that. Yeah, it is. That's very good. It is dependent on time, or is it?
Sometimes in the y direction.
Sometimes in the y direction. Okay. Does that make sense? Exactly. Right. Okay. So what is acceleration? Yeah. It's the change in velocity. Okay. And once you fire this thing out of the cannon or throw the ball or whatever, right? What's the only acceleration that's actually going on? That would be gravity. Which direction does gravity point? Or attract or whatever? Down. Okay? And therefore, there is only acceleration in the y direction, which means that the velocity is only changing in the y direction. What's the x velocity here? It's a constant. I am actually going to have you guys prove that as a task. Yeah. Oh, don't worry. It's not because you mentioned it that I've seen it. Yeah. You were going to do it anyway, right? Because I've given a variation on this problem. So the problem Cole is describing is it's basically like, so let's say that I have an object suspended from the ceiling, okay, and I have like a BB gun or something, and I rig the BB gun so that when I pull the trigger, the object that's suspended from the ceiling drops. So the exact instant I pull the trigger, the object starts falling. Okay? So the question is, should I aim higher than the object, at the object, or below the object so that I hit the object? What do you guys think? Below? At?
How do you see it?
Doesn't matter. So, let's say that the projector is the thing mounted to the ceiling, right? And I'm going to aim at it, right? I can aim below it, I can aim above it. But the instant I pull the trigger, it's going to fall, right? So we're like synchronized with the wire, okay? Should I aim at the target, above the target, or below the target? Which one you should do? So the physics department actually has equipment to do this demonstration, right? So they have like a thing that'll shoot like a tennis ball, and then they have like a stuffed monkey that they suspend from a thing. And so should you aim the tennis ball above, at, or below? What do you guys think? At? Pretty good. Good answer. Yeah. Okay. Anyway. So what we've noticed though is that the x velocity is constant, and when is the y velocity equal to 0? Is it? Well, okay, yes, but just the top, right? So at the peak, the y velocity is 0, and that makes sense because before the peak, which way is the object going? Up, okay, and also to the right. But then it hits the peak, and then it starts coming down. Okay, so if I were to graph this thing, well, first off, when would the peak occur? It'd be whenever the y-coordinate of this is 0. When does that happen? 9.8 over 5 root 2. Right? Isn't that obvious? Is it just like algebra bros? Yeah, okay. Exactly. Okay. So, great. So we can talk about the velocity. Yeah. All right, let me go back over to the iPad. And let's see, Elgato. All right. Because there's a couple other things I could talk about. What would the acceleration be? For this particular, for the projectile, yes. Well, yeah, any projectile. Okay. So what's the acceleration in general? It's the change of velocity, which means the derivative of velocity. What's the velocity? It's the change of position. So the acceleration is really, in a sense, the second derivative. Okay. For our projectile problem, what was the acceleration? Okay, careful. It was 0, comma, negative 9.8. Why? Because it's a vector, right? Which way does gravity point? Down, which means it has no x component, and its y component is, well, negative 9.8. That's just because of what the gravity here is on the surface of the Earth. Most of it, anyway. Yes?
So when you do the projectile motion, you velocity for x, or just in general, you know how like anytime angle it has like a y portion and an x portion.
Mm-hmm.
So if you write that, is that how you write that, like as a coordinate kind of?
Yeah, well, that's why I've got the cosine and the sine terms, right? Because I'm decomposing it into its two constituent coordinate directions, right? So yes, and the point here, this number 10 that's in my that was in the equations, is the initial velocity. So that would be like if we were talking about a firearm or a cannon or something, that would be the muzzle velocity. Okay, is the number that you would look up, right? Basically, how fast leaves the barrel of the firearm. Okay, or the, the, the squirt gun or whatever, right? It doesn't have to be a gun, but yeah. Okay. Yeah. So, all right. So, let's see, where was I going to go? Okay, so we talked about acceleration. We could also talk about concavity. Okay, and why would we care about concavity? Yeah, Jack. Yeah, so like why did we care about concavity back in top one? Yeah, so that told us when we were at peaks or valleys and maxes and mins and all of that. And in top one, concavity and acceleration were actually kind of the same thing, right? Because what was concavity given by in top one? First derivative. Is that true anymore? Sadly, no. Right? So things become more interesting when you do vector calculus. And as a preview of coming attractions, we could spend an entire semester doing calculus with vectors. Okay, and you can. It's called MAT112. How many of you, can I sell any of you guys on? Yeah? Okay. However, what's the one thing that's between you and MAT125, other than the final for this course? Linear algebra, exactly. Because in linear algebra, you study vectors in and of themselves. Okay? And by doing so, you learn the tools of working with matrices and vectors that allow you to maturely do vector calculus by having the tools of linear algebra at your disposal. Yeah, okay. All right, so concavity we can talk about. Could we also talk about arc length? Yeah, and the arc length formula actually in parametric is kind of nice. So what was the arc length formula in regular coordinates? It was this, correct? 1 plus the derivative squared dx. Yeah? Yeah? Okay. So that was sort of the version that we looked at when we had functions of the form y equals f of x. If we do it parametrically, oops, then it turns out to be this, which I like a lot better, personally.
Why does that work?
Why?
Yeah.
Well, it works because if you have a parametric set of equations, you can eliminate t by using algebra, and which means you can kind of convert back and forth between y equals f of x view and parametric view, with a few caveats, namely the algebra can get annoying, but yeah. Okay, now the reason I like that particular view of it is because what is my velocity vector? Well, if I have a position vector, let's say it's f of t, that's x of t, y of t, then the velocity vector is x prime of t, y prime of t. Okay, now let's go back to high school a minute, talk more about vectors. When you talk about vectors in high school, what were the things that you talked about? They are objects that have what? Direction. Okay, we talked a lot about that. What else do they have?
Something new, like something you said.
No, something you said. We just haven't talked about it too much.
Magnitude?
Yeah, they have a weight, the magnitude. How do you compute the magnitude of a vector? Huh? In various ways. It's like the most generic answer you can. No, there's precisely one way to do it.
Absolute value?
Well, okay, sort of, but it's a, yeah, it's a Pythagoras theorem.
Oh, yeah.
Right? Okay, so if I think of, I have a vector that has a component in the x direction, x prime, and a component in the y direction, y prime, what's the length of that thing? It's the square root of the sum of the squares.
Wait. What did you just write? You wrote 2 bars.
I did.
Absolute.
Okay, fair question. So
Conditional
Cole's
absolute.
making fun of me for writing 2 bars, 2 sets of bars. Huh?
I'm sure you're right.
Why do you think it's so personal?
I don't know. I feel threatened.
PTSD from your signal.
You're right about Cole.
Yes.
He's gonna take your job.
Well,
He's gonna take your job.
Yeah, once I get
I
those
don't know. I mean,
trigonometric
he could be like Tartaglia and Cardano and stuff. And like it could be like 16th century Italian mathematics, where the way you got a job was by challenging somebody else to a mathematical throwdown
That's like so
and
cool.
then beating them.
That's so cool. It's like a WWE belt.
Basically,
Why do you beat him up?
because that's so uncivilized. I mean, I'm sure there was plenty of that going on too.
You can't teach with a broken jaw, man.
Well, Tartaglia managed.
Wait, what?
Actually, Tartaglia means stammerer. So, anyway.
It's like a T4 down. I'm gonna come for your job.
Yeah, basically. I can solve a quintic equation.
Why?
Not really.
I know how to use mathematics, so then
Oh yeah, you take your mathematician. Name every mathematician.
name all of the maths.
All right, so point being, right, how do you compute the length of something? Well, if the vector, if we think of it as being a point that's some distance away from the origin, then what's the distance formula? Well, it's Pythagoras' theorem, basically, right, from the origin. Okay, so what do? I square each coordinate, I add them up, and I square root the whole thing. And that's exactly what I'm integrating to get my length. Okay, now, what the heck is with this double arrows business going, or sorry, double bars going on around here? Okay, so this is a distinction in terms of notation. If I write a single set of bars around something, what does that mean? Means the absolute value. If I put a double set of bars around something, it means the magnitude. Okay, and the difference is that absolute value, what kind of thing goes on the inside? It's already a scalar quantity, meaning it's a number, right?
Yeah.
But magnitude is something you do with vectors, right?
Yeah.
So numbers have absolute values, vectors have magnitudes, and we have 2 different notations to not mix them up.
Oh.
Okay, that's the distinction. Okay, so if you see a double set of bars like that, that means the magnitude, or sometimes it's called the norm of a vector. Okay, yes.
Why do we just use absolute values? Root of the direction
Well, I think fundamentally it's what I said, right? That absolute value is a function that takes in a number and outputs a number. The magnitude function takes in a vector and outputs a number. Right? So it's a different kind of thing, in a epistemological sense. Right? Yes, okay. So I'm not making up notation here. That really is the way we write it. Okay? And this is why I like that particular view of arc length better, because all we're doing is basically adding up, because it's an integral, right? Adding up the magnitude of the velocity vector over a range of t. Right? Yeah.
So is the derivative of a position graph, like the arc length, is that line going to be, like, is there a way to measure what the length of that derivative line is going to be? Or is it
The
just kind of like,
derivative vector.
right?
Yes, it's that square root that's at the bottom of the screen.
So is it going to be like from 0 to 10? Or is it
Okay. So, yes, okay, so good question. So, let's say that we wanted to know how far our projectile from the previous example traveled. Okay, there's two answers to that. You could say it's 10 point something because that's how far it went along the x-axis. Okay, but what's maybe a better answer, whatever the length of this curve is. Right? All right, so let's go back over to Mathematica and actually set that up. Okay, so do you guys see the distinction here? The range that it made it was 10 point whatever, right? Units away from our launch position. But how far did the object actually travel through the air? Do you guys accept that it would be given by well, sorry, let me call this. So I'm just going to define a function to be the derivative just to give it a name. Oops, I have to run that first. Okay, we do have one minor problem though, right? What does this number right here need to be? I just put 1 in for right this instant, but what should it be? It's neither, it's my t range. Okay, so if I want to know how far this thing has gone between launch and landing, I need to put in a t, the time at which it hits the ground. When did it hit the ground? Can you remember from last time? Well, we know where it hits the ground. What I care about is when it hits the ground. Yeah, well, okay, so let's recalculate that. Whenever the y coordinate is 0, okay, so what was the y coordinate? It was this, right? And we want to know when that is equal to 0, solve for t. Okay, and we get this. The other thing I'm going to do is, like before, okay, it was 50 root 2 over 49, and so that is the t value for when I land. And so if I integrate the norm of h of t, or h1 of t, excuse me, the norm of the derivative, from 0 to t equals 50 root 2 over 49, what have I computed? I've computed the length, the arc length, along the blue curve from the origin to when it hits the ground at x equals 10 point whatever.
So if x from 10 to x equals 0 to x equals 10 point whatever, that's not the distance.
Right. That's the range it went. But the actual, okay, so draw a straight line from the origin to this point at x equals 10 point whatever, right? What's the length of that line? 10 point whatever. Okay. Do you agree that the blue curve is longer? Yeah. What we have computed is the length of the blue curve. So, like, that's how far actually the thing went in the space.
Straight
Minimum. Right. Because what's the shortest distance between 2 points? Straight looking line. Okay. So yeah. So the range of the projectile, meaning how far away did it hit the ground from where we launched it, was 10 point whatever meters. The actual flight distance was 11 point whatever meters. Okay, does that distinction make sense? Yeah.
So you're doing arc length here, you said?
Yeah, that's what we computed.
But where is the square root?
It's built in. So right here where I did, let me highlight it so people at home can see. This is the derivative function, right?
Yeah.
Okay. Well, what is the norm of the vector? It's the square root of the sum of the squares. Well, how do you get the length of the vector? Pythagoras theorem, right? You take the square of each thing, you add them up, and you square root the whole object, right? So I didn't explicitly write the square root because
So you're just putting the function
because I used the built-in function norm to do that for me, just so that it wouldn't look ugly on here. No, not really. I just used in the built-in function. Okay. Well,
If I just write that on my paper. So the norm is just like a verb for it just basically like norm means I'm gonna multivariate theorem.
yes, exactly. The norm of a vector means Pythagoras' theorem, right? And yeah, so I just did that to my formula that I was typing in Mathematica, wouldn't be like 6 miles wide, right? But you get the idea, right? The square root is built into this. I like that verb, norm. Okay. You saying the word verb.
Norm is the verb of Pythagoras theorem.
Yeah, verb for Pythagoras theorem. Yes. Okay. So, yeah. Okay, so does that kind of make sense? All right, so at this point, I think the best thing to do is to turn you guys loose on exercises. So, you guys know how that works. Right? All right, the other thing is what's happening on Monday?
No class.
Yeah, an excellent do be proud, gentlemen. I look forward to you guys demonstrating your excellent knowledge. Okay? All right, well, I will see you guys later.